Uh, in this lecture, we will study Sylows theorem. Sylows theorem. Some of the basic concepts we need. Sylows theorem. To study this theorem, we need few of the definitions and few of the results which are more important, जो हम लोग इसमें use करेंगे while proving this. So some of the result you must know before going for a proof. We must first is uh, class equation. You must know the class equation. Second is you must know mm, Cauchy's theorem. Cauchy's theorem for abelian group. For abelian groups. Third is a result. A result says a result. A belongs to ZG. A belongs to ZG. Then H generated by A is a normal subgroup. Normal subgroup of G. Then fourth is concept of quotient group. Group order of G mod H is equal to order of G by order of H. Fifth, N of A is a subgroup. Is a subgroup of G, and then so these are the few of the results which are needed in the proof of Sylows theorem. So of course, there is one more thing, concept of ZG, that is center of a group. Center of a group. So these are the few of the concepts you must know before proving the Sylows theorem. So let us talk about definition first. Silo P subgroup. What is Silo P subgroup? A definition. Definition. Silo P subgroup. What does this mean? Let G be a finite group. Finite group. And P be a prime number. So that P raised to power K divides order of G, but P raised to power K plus 1 does not divide order of G. Then any subgroup of G, subgroup of G of order P raised to power K is called Silo P subgroup. Silo P subgroup. Okay. subgroup of G. In other words, in other words, in other words, order of G is equal to finite. Order of G is finite. P is prime. P is prime. P की k power divides G, order of G, but P की k plus 1 does not divides order of G, order of G. Then any subgroup group of order p raised to power k is called Sylow p subgroup group or PSSG PSSG group. So this is called Sylow p subgroup. साइलो पी सब ग्रुप का मतलब क्या है? जी फाइनाइट होना चाहिए, पी के अगर इसको ऑर्डर को डिवाइड करता है और पी के प्लस इसके ऑर्डर को डिवाइड नहीं करता, तो एक सब ग्रुप होगा जिसका ऑर्डर कितना होगा? पी रेस्ट टू पावर के। ऐसे सब ग्रुप को हम लोग बोलते हैं पी साइलो पी सब ग्रुप। और इन अदर वर्ड्स, अगर ऑर्डर इज फाइनाइट, पी इज ए प्राइम, पी रेस्ट टू पावर के डिवाइड्स ऑर्डर ऑफ जी, बट पी रेस्ट टू पावर के प्लस 1 does not divides order of G, then any subgroup of order pk is called Sylow subgroup. Also, sometimes we define Sylow P subgroup as follows. Sometime क्या होता है, हम लोग ऐसे भी डिफाइन करते हैं। वो क्या है? अगर G क्या है? G be a finite group and order of G is equal to P raised to power K Q, where P and Q is equal to 1, P is prime, then a subgroup H of G is called Sylow P subgroup, if and only if Sylow P subgroup if and only if order of H is equal to P raised to power K. Order of H क्या है आपका? अगर P raised to power K है, and we say that this is a Sylow P subgroup. Now we are in a position to state Sylow first theorem. This is Sylow's first theorem, or one can say the first Sylow theorem. So its statement is statement. Let's talk about its statement. Let P be a prime number. Let P be a prime number. So that P raised to power K divides order of G, where K belongs to positive integers. So this is a positive integer, one natural number. Then G as a subgroup of order subgroup of order pk. This is that a p is a prime. P raised to power k divides P is a prime and P raised to power K divides order of G, where K is in positive integer. Then G as a subgroup of order P raised to power K. So we can see here, for example, we can take an example. For example, order of G is equal to 27. So we can write here uh, 4 into 28, sorry, 4 into 7. So this can be written as 2 ka square 7. Then we say that because 2 divides order of G, this means that G as a subgroup of order 2. 2 square divides order of G. It implies that G as a subgroup of order 4, and 7 divides order of G. This implies G as a subgroup of order 7. And this is the meaning. So this is the meaning of Sylows' first theorem. If there is a prime, that prime raised to power something divides order of G, then G as a subgroup of order P raised to power that number. So this is how the Sylow theorem is stated. Now we will see the proof of this theorem. Proof. Let's talk about the proof here. So we will prove this. We will prove this theorem with the help of mathematical induction, mathematical induction method, right? On order of the group G, that is order of G, right? So let us take when order of G is equal to 1, then what happens? Order of G is equal to 1. Now 1 divides order of G, and E is a subgroup of order 1. So nothing to prove. Nothing to prove. When order of G is equal to 2, then what happens? Then obviously 2 divides order of G. Let H be a subgroup of subgroup of G, so that order of H is equal to 2. Since every group is a subgroup of itself, so therefore this implies H is equal to G. So therefore there exists a subgroup of order 2. So we can assume the induction hypothesis. This implies the result is true for order of G is equal to 2. Now we have shown for order of G is equal to 1 and order of G is equal to 2. Now we will take the induction hypothesis. Induction hypothesis. Now let the result is let the result is true for all orders, all groups of order less than order of G. Now we shall prove the result for order for group of order equal to order of G. Let's talk about this. Now there are two cases here. Now there are two cases arises. Now there are two cases arises. Case one is G has no proper subgroup or G has a proper subgroup, right? So these are the two cases which are going to come because G can have subgroup or G may not have any subgroup. So we'll take case one. When G has no proper subgroup and p raised to power k divides order of G. Now, G has no proper subgroup. Therefore, the only subgroups of G are E and G. But p raised to power k divides order of G. This implies that only subgroup. So only subgroup of G is G, say that order of G is equal to p raised to power k. So therefore, the result holds in this case. Okay. So in this case, we are getting a subgroup which is itself of order p raised to power k because it is not having any proper subgroup. Case second. When G has a proper subgroup. So this is what we have. So let's करते हैं. And pk divides order of G. Now let's करते हैं H be a proper subgroup of G. No, H is a proper subgroup of G. This means order of H is always less than order of G. This one thing is clear. Order of H is always less than G. Now there are two cases. One H or so P divides P raised to power K divides order of H or P raised to power K plus 1. Sorry. P raised to power K does not divides order of H. So there are two cases within this case. So we can take subcase 1. When P raised to power K divides order of H. Now, H is a proper subgroup of G. This implies order of H is less than order of G. So we are getting induction hypothesis. Now, K divides order of H and order of H is less than order of G. So we have the induction hypothesis. Induction hypothesis says result is true for all the groups of order less than order of G. जितने भी order G के छोटे ग्रुप हैं, G से छोटे ग्रुप हैं, उन सब के लिए ये रिजल्ट होल्ड करता है. So this means that there exists a subgroup H1 of H such that order of H1 is equal to P raised to power K. Now, H1 is a subgroup of H. This is a subgroup of G. This means that there exists a subgroup H1 of G such that order of H1 is equal to Pk. Hence the result. Now we will see that. Now we will consider the case when Pk does not divide order of H. When subcase 2. When P raised to power K does not divide order of H. Right? So we will talk about the normalizer and class equation. So we know that also H is a subgroup of, proper subgroup of G implies H is not equal to G. Fine. This is what we have. Now here we will use the class equation. We know that order of G is equal to order of ZG, center of G, plus summation A don't belongs to ZG, order of G divided by order of normalizer of it. Fine. This is what we have. Now, A don't belongs to ZG. This implies N of A is not equal to G because there is a result. That result says if A belongs to ZG, if and only N of A is equal to G. So the other way around also holds. This means that N of A is a proper subgroup of G. Now we have the case that Pk does not divide H, where H is a proper subgroup of G. This is any subgroup of G. This means that Pk power does not divide N of A. Pk power does not divide N of A. Now we know that order of G can be written as order of G by order of N of A dot order of N of A. Now this does not divide N of A. Now Pk divides order of G. It implies Pk power divides order of G by order of Na, but we just shown it does not divide Pk power does not divide N of A, order of N of A. Sorry, this is order order of n of A. So pk does not divide order of n of A. This means, this implies pk divides order of G, order of n of A. Now, let it be equation 1. So we'll let it be equation 1. No, using this class equation. Now, this is not holding for this p raised to power k does not divide this. So we can write this pk does not divides does not belongs to zg, order of G by order of Na. So we have seen that. So therefore we have pk divides order of G, pk divides order of G by order of n of A, summation A belongs to Zg. So from class equation 1, क्लास इक्वेशन 1 से हम क्या करेंगे, इसको इधर ले आते हैं, ये इसको और इसको सब्ट्रैक्शन को डिवाइड करेगा. सो दिस इंप्लाइज दैट पी की के डिवाइड्स ऑर्डर ऑफ जी माइनस समेशन ए डोंट बिलोंग्स टू जेड जी order of G divided by order of Na. So this means if we are transposing this to this side and we are getting order of Zg, this means P ki K divides order of Zg. Fine. So this is what we are getting. So we got order of Pk divides order of Zg. Now, so Pk divides order of Zg, which is abelian. Okay. So there exists an element B belongs to Zg such that order of B is equal to P raised to power K. Sorry, order of B is equal to P. This is given by, this is using Cauchy's theorem. Cauchy's theorem for abelian groups. Cauchy's theorem for abelian group. So that says, so Cauchy's theorem की statement ये रहती है, if G is a finite abelian group and P की K divides order of G, then there exists A belongs to G such that order of A is equal to P. This is the theorem, Cauchy's theorem. So Cauchy's theorem for abelian groups. So we have used this. So we have got an element whose order is P. So let H is a group generated by B. Then this is a cyclic group, and B belongs to Zg. So in the beginning we talked about a result. So we use this using this result. This one, third one, that is A belongs to Zg. Then H generated by A is a normal subgroup of G. So we have H is a normal subgroup of G. So this means that G mod H is well defined. So G mod H is well defined. That quotient is well defined. Now order of G mod H can be written as order of G divided by order of H. So obviously order of G is divided by something. So this is less than order of G. This is always less than order of G. This means that order of G mod H, this is always less than order of G. Fine. So we are getting the, so what we are getting? So we have got order of G mod H is less than order of G, and P raised to power K divides order of G. This implies P raised to power K minus 1 divides order of G by also, let me do this properly. Now, P की K power divides order of G. This means that P की K minus 1 divides order of G divided by P. And so we have taken here. Now, because this is a cyclic group, so order of H is what? Order of H is equal to P. This is equal to this because this cyclic group में क्या generator और उसका group का order same होता है. So order of H is equal to P. So just putting up P raised to power K minus 1 divides order of G divided by order of H, and this can be further written as Pk minus 1 divided by order of G mod H. So we are getting what? So we have got P raised to power K minus 1 divides order of G mod H, and order of G mod H is less than order of G. So again the induction hypothesis get active. So by induction hypothesis, this is because if the order is less than this and P raised to power something divides order of G, there exists a subgroup. So this means G mod G as a subgroup. There is a subgroup H1 divided by H of G mod H such that order of H1 by H is equal to P raised to power K minus 1. Here H1, H is containing H1. Here H is containing H1. Now order of H1 by H is equal to P raised to power K minus 1. So order of H1 is equal to P raised to power K minus 1 dot order of H is equal to P raised to power K minus 1 P. This is P raised to power K. Therefore, order of H1 is equal to P raised to power K. Now, H1 is a subset of subgroup of G. Therefore, there exists a subgroup H1 of G so that order of H1 is equal to Pk. So we have shown that whenever, so therefore the result holds. So in all the cases, if P raised to power K divides order of G, then there exists a subgroup H of G such that order of H is equal to P raised to power K. Hence, the result. This is called Sylows' first theorem, and this is how we prove. Thank you.